This lesson is on reference frames and changing from one reference frame to another. Before we get into that, though, if we start with a relative velocity problem, because the two kinds of problems are related. If you imagine driving north at 30 miles per hour and your friend drives south at 40 miles per hour, what is her velocity relative to you? Well, this is a classic friend relative to you is the velocity of the friend relative to the ground, plus the velocity of the ground relative to you. Of course, the ground relative to you is the positive or the negative of the you relative to the ground. So the ground is heading 30 miles per hour south if you're heading 30 miles per hour north, and that gives us about 70 miles per hour south. The follow-up question would be, does the answer change after the cars pass each other, after your friend passes you? And the answer to that is no, right? The equation is exactly the same. It's true that the picture would shift, right? The red car would move to the left and the gray car to the right, and they're now moving apart from each other. That's the speed at which they're separating instead of the speed at which they're approaching, but the answer is still the same. So in this video, we're going to look at changing reference frames and do a little practice with that. And what this does is it really gives us the ability to solve some problems much more easily. Not all, but some. So reference frames are actually a really key concept when it comes to sort of our historical understanding of the universe. If you know the story of sort of the Middle Ages in Europe and Galileo and Copernicus and how that all changed from what was believed from the Ptolemaic universe, you know that the idea that Earth being at rest, a velocity of zero and everything measured relative to the ground, that was sort of the true velocity, or was considered that. And Copernicus was willing to say, oh, well, the Earth orbits the sun and everything else is going around. But the distance to the sun and all of that was well known. And so you could calculate pretty well that the Earth is traveling quite fast, 60,000 some miles per hour. And of course, we know that when you travel quickly, you kind of have these effects of wind blowing in your face. And so that didn't seem to fit with the worldview that a lot of people had at the time. Galileo says, well, we can test this, right? And Galileo, if you remember from Free Fall, also said, well, all of this works if there's no air resistance. And that was a piece that people often left out when they were thinking about it. And so he said, well, let's imagine that you're just dropping a cannonball from the mast of a moving ship. The cannonball is good because it's a dense, heavy, spherical, smooth object, so air isn't going to affect it very much. And he said, well, if that's what you do, then the observer on shore, if you release the cannonball, sees it follow a projectile path because it has an initial x velocity, and then it moves along. On the ship, you would just see it drop straight down onto the ship's deck. And if you've ever taken a ball, taken something, dropped it, moved it, thrown it up in the air when you're in a moving vehicle, you've noticed this, right? So the observation was being on the ship was just like being on Earth. As long as everything is moving relative to the ship and we're not outside of that ship, we can't really tell about the other motion. So this was early into the idea of understanding inertia. And inertia, which we'll get to in a big way when we talk about forces, is the tendency of an object to stay in motion if it's already in motion. There's more to it than that, but things aren't just going to abruptly change their motion because you suddenly let go of this. We talked about this in our free fall problems, right? A hot air balloon ascending and you drop a package. Well, that means that the hot air balloon's upward velocity is the initial velocity of the package. And so again, if you imagine tossing a ball while standing on an escalator, or standing in an elevator while it's moving, right? Especially an elevator, you're completely enclosed and you don't really have any idea that you're moving except at the beginning and end when there's some acceleration. So this leads us to a definition. We say inertial reference frames, all inertial, which means not accelerating. So that elevator is only a good example when it's traveling at a constant velocity in the middle of its run. Escalators are good for this and so on, are equally valid. So you can talk about it inside the elevator, outside the elevator. It's all the same. You might get certain different numbers, but you'll come to the same conclusions. So what can we do in a perfectly inertial reference frame? Well, also known as a Newtonian reference frame. Well, there's some things that you're going to get different measurements of depending on your reference frame. Velocity is one. Kinetic energy and momentum, which we'll learn about later, depend on velocity. So those will be different. But on the other hand, you will always agree, no matter which reference frame you're in, is how far away 2 points in space are, the time it takes to go from one point to the other, and the rate of acceleration. And therefore, the laws of physics will still be valid regardless of which reference frame you look at. And so kind of our summary statement is that in Newtonian physics, that is sort of classical physics that we're looking at now, time and space are absolutes. The amount of time it takes and the distance you travel are not things that change just because you're looking at it from a different perspective. If you're thinking, didn't Einstein say something? I said, yes, but that's not Newtonian physics. A little bit more on that later. So that leads us to an example. We've got two cars heading towards each other. Cars A and B accelerate towards each other on a flat, straight road. They collide at time equals 4 seconds. Now, what we know is that the velocity initial of each of these cars is given. And we've got the acceleration rates of each of them. And then they're going to collide. Now, you might ask the question, how far apart did they start? Now, I've just gone and said inertial reference frames where things are not accelerating are all perfectly valid. And then I went and provided some acceleration rates. It turns out we can solve some problems like kinematics problems, even if there is a relative acceleration. If we switch to car B's reference frame, we can say, well, the velocity of A relative to B, at least initially, is 30 meters per second, right? They're getting closer together at 30 meters per second. And the acceleration of one relative to the other is positive 8, right? And so if we put all of that together with the amount of time we are given, 4 seconds, we can solve a kinematics problem. And now it's just a simple kinematics problem. X final equals x initial plus v initial t plus 1/2 at squared, 184 meters. Now, if you were to try to solve this in the ground reference frame, the one we're sort of observing from, you would have had to set up a system of equations and said, well, they arrive at a particular place at a particular time, but at that time, but you wouldn't have known their final velocities, and you wouldn't have known a few other things, right? We don't know how far apart they are, so that becomes a little bit more complicated. Now, when the inertial reference frames or the reference frame is non-inertial, you have to be a little bit careful. It can be dangerous to use them because the laws of physics don't apply, but they give us some interesting information. So we're going to proceed with caution and look at an example here. So if you think of Dorothy and Toto falling out of a hot air balloon, right? A hot air balloon right there. What is their velocity with respect to each other 2 seconds later? Well, a couple things to think about. It's 0 meters per second, right? The velocity of one relative to the other. And the reason for that is they accelerate down at little g the whole time, right? So their acceleration rate is 0 meters per second relative to each other. So they keep gaining speed at the same rate relative to the ground, and relative to each other, they never have any difference in velocity, and their acceleration is not different either. So we could do another thing. You're in an elevator, minding your own business, you have a ball, right? If the elevator cable were to snap, and you go into free fall, right? What will the ball do if you let go of it? Well, if you're in free fall and you let go of the ball and there's nothing else touching it, it will also be in free fall. So it'll just float beside you and you will fall together, right? You could ask another question. This is an absurdly long elevator shaft, so we don't have to worry about this, no friction. And we might say, well, what if you want to throw the ball around and see what it does? Well, if the acceleration of the ball relative to you in the elevator is 0, it just travels in straight lines. If you throw it to the side, it goes to the side. It does not look like a projectile to you. However, if the elevator was glass and the shaft was glass and someone was watching it, the ball would follow the free fall path, the projectile trajectory you would expect, right? So conceptually, we might think about this. If you drop balls A and B at the same time, and let them free fall. One is 1 meter above the other. What will happen to the distance between them as they fall, right? Will it increase, decrease, or remain the same? Well, we have a couple things to think about. The initial velocity relative to each other is 0, and the acceleration relative to each other is 0 as well. So their velocities will never increase relative to each other. So the spacing between them will remain the same. And you can test this by simply, you don't have to do the free fall example. You can also just get a ramp and release 2 balls and watch that they roll down the ramp together. And that's a demo that we can do when we're back in class together. So because they have 0 velocity and acceleration relative to each other, they never go any farther. All right. What if you drop ball A from rest, and then 1 second later, you drop ball B? What will happen then? Well, what's the difference now? They still have the same acceleration relative to each other, but there is a relative velocity because ball B started traveling, was at 0. And so from ball B's perspective, A is already moving. So even though they're going to speed up over time, the distance between them will increase because ball A and ball B will have a relative velocity, even though they have no relative acceleration. Same idea with the 2 balls on the ramp, right? If you imagine releasing one and then releasing another one later, right, they're going to have a difference in velocity as they both speed up, and one of them will continue to pull away. All right, so wrapping up here, the frame of reference allows you to look at things from different perspectives, and sometimes it allows you to solve a problem more easily. The biggest example that we looked at so far is if 2 objects are accelerating, you can often look at what's happening relative to each other without considering the acceleration at all, which ends up being a very simple problem indeed.